different scale. Basically, you could say I'm interested in multi-scale phenomena, and they happen at all spatial temporal scales, from galaxy formation to epitaxial growth to cell aggregates. But today, I will only focus on this specific category, which is where the physics happens at the bulk, and you have some interfaces that is regulating the transport processes, which takes us to a short introduction to interfacial transport processes. Well, basically, for interfacial transport phenomena, I mean whenever you have some interface which is separating a two-phase, maybe medium or heterogeneous environment, and you have transport of momentum, mass, chemical species, energy, electric current, or charge that happens across an interface. Especially, I will be focusing on epitaxial growth as an example of transport of mass across atomic island boundaries. And I will talk about electroporation, which is the transport of electric current. Another thing that one aspect of this of everything that we do is that the mathematical models that we use are themselves multi-scale models, in the sense that where we idealize the interfaces as some sharp 2D surfaces in 3 dimensions, and they will provide some boundary conditions to the governing PD everywhere else. And these are multi-scale models because, as you can see in this example, for example, you see a bilipid membrane, but the effect, if you want to be very faithful to the physics, you have to run a molecular dynamic simulation in tandem with the continuum simulation, but that's not what we do. We just use some coarse-grained model instead. So the reason for that is because, well, the macros, this is, of course, it's computationally very difficult to do that, to consider the accurate macro scale models. So instead we just, and also the usual macro scale models that people use, which is, for example, let's say people usually, in the case of cell aggregate operation, they just assume an effective conductivity for the whole environment and then do a bulk simulation, which is not very accurate. So we don't do either of them, we just go somewhere in between, which is a compromise between the two. So now let's start from the computational framework that we use at Castle. So basically, every simulation that we do has 3 major components. The first one is the level set method, which is the implicit representation for the interfaces. In the top right, you see this red function is a scalar function, which is defined everywhere in this domain. And you just see that the zero contour of that function represents where the interface is located. So you can see that these two, let's say, bubbles are growing in time and they start to merge, and that motion can be captured in the evolution of level set function. The other aspect is adaptivity, because all the physics in this kind of problems happens on the sharp interfaces. You want to have higher resolution close to the interface. For example, here you're looking at an ellipsoid and the quad tree, and there's this arc tree which is refined closer to the interface, and you have maximum resolution here. And then you have the tree. The third component would be how you partition it among processes, for which we use Z ordering, which is provided by the P4S library, basically. So this specific combination is very useful, powerful for tackling the type of problems you're interested in. So a little more detail about each of the components. So the level set function basically is defined everywhere in the domain, and at any point it encodes the minimum distance to the surface of the object that you're interested in. When your outside is positive, with your inside, it has a negative sign. So it's a signed Euclidean distance function. When you have that function, it has some nice properties. For example, you can get the normal direction by computing its gradient, or computing the divergence of the gradient, and gives you the mean curvature. Another aspect which we use in, for example, Epitaxial is that when we want to be able to evolve this interface, for which we usually have some physics that tells us where the velocity comes from, and then we can compute it from that, the conservation of mass equation, or whatever, and then we just plug it here and evolve at the level set function. About the adaptivity, I just want to introduce some concepts and some terminology we use. Let's say we start from the whole computational domain is the zeros, is the root of a tree, and we call that to be at level 0. And every time we decide to split the box into 4 or 8 pieces, we introduce another level. In this case, this is a quad tree, so every time we have 4 new children. And the refinement criteria is given by the value of the level set function on the vertices of the box. So basically, this specific equation enforces to have higher resolution closer to the boundaries. And the partitioning gives you something like this. Let's say you have, this is one snapshot of my epitaxial simulation. Every one of these is an interface, and these high resolutions are focused around interfaces which are spread everywhere in the domain. As you can see farther from the interface, you don't have any, it's coarse-grained, it's coarser, but closer is refined. And the different colors are different processors. This is the global tree, which is spread on all processors, but every processor itself has a local version of it, which just the leaves here are match the ones in the global tree, but everywhere else is just arbitrary to be able to build these leaves here. So let's focus on epitaxial growth, just attributions first. This is a joint work with R2 Gritted, Daniel Boschkoff, Joshua Schneider, Dio Margetis, Christian Rasch, and Friedrich. And it was published in Journal of Computational Physics in 2018. Epitaxial growth is basically when you are depositing some atoms on a substrate, and these atoms then find each other to form these islands, and these islands then can have different morphologies. For example, you can have these mounds in this case. Every disk that you see here is an island, and they can be put on top of each other, which gives you these mounds. Or, for example, you could have some bigger things like steps and step edges. Different morphologies can happen. These are very important from the point of technological applications. There are a lot of optoelectronic devices that use epitaxy as the main fabrication process. For example, transistors are made as such. And you want to be able to control the formation of these mounds because they can degrade the electric properties of these devices. What we did was we developed a conventional approach for some parallel simulations of epitaxial growth on time scales and length scales that are relevant to these devices in the first technological domain. So first, a little bit about malformation is that, so there are two main types of growth for epitaxy. Here we are looking at layer by layer growth, which is when you're close to the thermodynamic equilibrium, or when you're far from thermodynamic equilibrium, you get these mound formations. So the physics of it is known, it's just how to solve them in larger scales. The main challenge is that, of course, the atoms are hopping around at time scales that are some microseconds and length scales that are angstroms. But these devices are some microns in lateral size, and the fabrication process takes on some seconds to minutes. So you see that there are orders of magnitudes in difference. So one avenue, as I said, is using multiscale models, and this is called the island dynamics model in the case of epitaxy. Here you're looking at some atoms. Let me just an overview of epitaxy in more detail. It's just that these atoms are deposited as shown in A on the substrate. When they fall in the substrate, they hop around randomly. It's random walk, basically. That's why the model has this diffusion part. And they could find each other and form a dimer. This dimer could be stable to grow these islands, or it could be unstable and break apart. So, or they could just find the islands and attach to these bigger ones, and this process goes on. One important aspect is that at these boundaries, you have some quantum mechanical effect. And basically, when you're falling from, when you try to go down a terrace, you see the energy landscape looks like this, which is so you have a stoppage barrier basically. So it's less likely to go down than just go the other way. So, and that leads to this Early-Schubel boundary condition, which is basically a Rabin type boundary condition. And when you're at thermodynamic equilibrium, the other boundary condition you have to impose here is just this Dirichlet. So the governing equation is the diffusion type equation as shown here. And this n is the island density, which is the number of islands divided by the size of a domain. And it's computed deterministically by this equation, but the stochastic part comes in about on the location of nucleation. So you will randomly decide where to nucleate the new islands given a profile distribution that follows a distribution function that looks like rho squared. So at every time step, you have to compute the rho squared and then draw a random location. Then you have to also complement this model because we're going with a velocity, as I mentioned earlier, because we're going to use the Lorentz function, and that's a conservation of mass, the difference between fluxes on each side of the island boundaries this here. So I will skip this one. If you want to discuss it, we can discuss it later. There's for the representation of these islands, we just bundle every island at each layer by one level set function, and whenever we have a new, let's say, layer that grows, you introduce a new layer, and when one layer is fully covered by atoms everywhere in the substrate, we recycle that array and we reuse it for the next layer. So that's more efficient in terms of memory usage. And then we have to, so now that we have bundled everything together, we have to be able to identify them. The other alternative would be define one level set function for each island, but that would need to require thousands of level set functions defined everywhere, which is very that's just impossible. So now for the numbering, the only issue is that you're doing it on a parallel environment, and you have to be able to communicate the island numbers and the ghost layers around each processor. So for example, so what I'm saying is that every processor in different color here has its own part of the domain and numbers them uniquely as it has, and it just recursively looks out the neighboring and gives the same number. And on the ghost layer, they communicate the number and they end up with a global numbering. So now let's look at the, now that we know how to represent the domain and the features of the domain with a Bessel function and how to communicate the identification, things like that, you should be able to solve the actual equations, for which we use a Crank-Nicolson scheme in time, and the discretization is given here. The only difficulty here is to treat this diffusion component, and we use a hybrid approach when we are far from the interface. For example, this is a part of an island, and this is the boundary of the island. The shaded area is the island, the interior of the island, and that's the out exterior. So because the grid is adaptive, when you're far from the island boundary, you can have some T-junctions like this one, which means that you don't have a direct node on the right-hand side, in which you have to interpolate the value of this ghost density value here according to the neighboring node values. So using just the finite difference method, this region far from the boundary is given. You can just discretize far from the interface, but closer to the interface, you have to use a finite volume scheme, which is basically integrating over on this computational cell. You just integrate over this domain and then use the divergence theorem to project everything on the fluxes on the boundaries. And unfortunately, on this side, the flux is actually just given with the Rabin boundary condition, just replace for it. And the rest is just details on how to compute the value of this rho gamma, for example, that appears here in this integral, by Taylor expansion from this node towards the interface, and for which you actually need to compute the gradient of the Bessel function, which is easy to do. Anyway, so the rest of it is just straightforward. It's from finite volume, and we can compute the rest of the edges of this box, this cell, just straightforward, as you see. Now, when you impose the Dirichlet boundary condition, one way is to take the limit of d prime to d, because that would the Rabin boundary condition will just go to become the Dirichlet boundary condition, but that is numerically not robust. Instead, we just use this dimension by dimension discretization strategy, which is basically to interpolate, basically replacing the diffusion operator with this equation, for which you need to know this rho g, which is this one, and you just use this quadratic extrapolation given the values that you want to impose. The Dirichlet value on this interface is given, and these two are also known. So basically, you just fit this function and extrapolate what's the other one, and you do it in every dimension. So now we have discretized all the equations and considered the boundary conditions, both Dirichlet and Rabin, and you have a linear system which you can solve with PETS. After you perform the solution, you get the density field at each layer. And now you want to be able to advect the Bessel function, for which you need to compute the velocity field. And as I mentioned, this is just the continuity of mass as is given here. Again, because we are not adaptive grids, we use a corresponding finite difference formula for computing these gradient terms in the x and y directions. And then we compute the velocities. To advect the Bessel function, we use a similar Lagrangian scheme. The main importance of this is that this doesn't have a CFL condition, it's unconditionally stable, so it doesn't limit the time steps that the simulation has to take. And there are some more details about, for example, let me show you this video. When the interface is growing, you see that behind the interface, you're going from a higher resolution to a lower resolution at all times, so you have to interpolate, but that is straightforward to do. The trouble is how to interpolate ahead of this wave, this interface, and because you're going from a coarser grid to a finer grid, for which we just do these this non-oscillatory quadratic interpolation scheme. Okay, so now this was all it takes for the computational aspect, the numerical aspect, the algorithm-wise. Now let's look at some efficiency tests. This is a weak scaling test where the computational work is fixed. It's just increasing the number of processors and see how, by doubling the number of processors, how much less time it takes to perform the simulation. ideally you would expect to get, by doubling the resources, you would expect to get half the time, but that never happens because of communications. But the point is that it should be up to a very high number of processors, you should get very good scaling here, and that's very good. And the other aspect was, for gaining some performance, was mesh adaptivity, which is basically attained by keeping the resolution, the maximum level of refinement, which is at the interface fixed, but instead lowering the minimum level of refinement, which is farther from the interface. And here we're showing that by lowering the minimum level of refinement from 8 to 4, you get some 8 times increase in performance. So time is less by a factor of 8. Now, besides the accuracy, besides the efficiency of the method, there's also the issue of accuracy. You test that because these are, every time you run the simulation, you get a different morphology. It's on a statistical test, which is kind of benchmark for these kind of simulations. You basically compute the surface area of these islands and normalize them according to some function, and it has to fall into this universal distribution, which is, and it should be independent of the parameters of the simulation. So no matter what are the diffusion coefficient or the flux of the depositing of the atoms, you should always get the same thing. And this is actually, they all collapse on each other, all of our simulations. And this is the previous work in this field, which was in 2002, which is a serial version of a Monte Carlo simulation. And they are also in agreement. So just some visualizations to show the size of the domain. So this is 1,000 lattice points in every dimension. And this is actually the size of actual devices on the micron in every dimension. And you see that the resolution is high enough to resolve the dimer, which is 2 atoms on the topmost layer of this specific island. And also you have enough resolution everywhere else. Also in the Rabin boundary condition, you would expect to get these mounds. And this is a representation of the level set function, which looks visually similar. And we also checked, of course, we just showed you that this is also produces statistically meaningful results. And this is the density profile. And the point here is that on these islands, there's just one issue, is that these islands are too steep compared to, not too steep, but steeper than what you should expect to get in actual things, because but that's known because the model doesn't take into account some downward transport processes. But the point was to build this building block for adding more physics to it. And this is doing a fair job. And now you can also play with some parameters and for example, verify that as you decrease the barrier size, going from here to here to here and there, you go from mound formation to layer by layer growth. As I said, when you take the limit of D prime to D, which means this ratio should be closer to 1, you should expect to get a more Dirichlet type boundary condition, and that's what's happening too. So this allows for doing some sort of post-processing and also answer some scientific questions. This was my first work that I did with other people that you can see here. And this was published in Journal of Computational Physics in my first year. The next project is about electroporation. And this is a joint work with Arthur Guittet, Claire Poignard, and Frederick Gibault, also published in Journal of Computational Physics in 2019. So let me start by introducing what electroporation is. It's basically a restructure. So let's say you have a cell membrane, right? And you apply an electric field. And because of the electric field, there will be a pore created on the surface of the membrane, and this pore will start to grow over time. And this schematic here shows what happens. For example, here there's no electric field. You apply it, and 0.1 nanoseconds later, you have this water wire. These blue molecules, these are water molecules. And then the colored ones are the ions in the environment. As time goes on, this starts to widen, and there will be more ions moving through the membrane. So it's basically, so electroporation is electric and so that's what you're looking at. Usually what people do is performing some Monte Carlo molecular dynamics simulation, and this is some snapshots that I took from some review paper. But again, the task that we had in mind was actually to simulate not a segment of a membrane, but actually tens of thousands of these cells, and to look at what is the statistical properties of a cell aggregate. And also look at not only just the statistics at equilibrium after they equilibrate with the electric field, but also how they evolve towards that equilibrium, because experimentally there were some results that, for example, showed that the time evolution is not exactly exponential profile. It goes from a fractional exponential profile, and the fraction of the derivative actually corresponds to healthier and unhealthier state of the tissue. So there were type of scientific questions that we had in mind when we started this project. But Generally, electroporation is, of course, widely used for 250 years. And in the last 20 or so 40 years, people have started to use it in medicine. For example, for electrochemotherapy, for cancer treatment, for gene electrotransfer or DNA vaccination, and also non-thermal reverse electroporation or transdermal drug delivery. And I'm just showing an example of transdermal drug delivery, which is here you have some medicine, which is some drug which is in cyan, and this is some skin of a pig, basically. And you apply an electric field, it starts to penetrate deeper than when you don't have an electric field. So it enhances permeability, basically. People use it for transmitting drug to the body without actually using the needle. So, but going back to the modeling part, the model that people usually use is associated to Krasuska and New in 1994, which is quite widely used, but it has many shortcomings. For example, the characteristic time scale of porturiation in the Krasuska and New's model depends on the membrane voltage, and it's not an intrinsic property of the membrane, which is physically wrong. The second issue is that pore density in their model is unbounded, which is mathematically wrong, physically also. And also, most important one is that there's only one time scale in that model, and it is several seconds. But the experiments show that there are two time scales in electroporation. One of them is a few microseconds, that corresponds to pore creation and pore resealing. And that is associated with an enhancement of the conductivity of the environment. And there's a second time scale, which is about several minutes, and that is a more mechanical transport of the molecules, which is enhanced for that long, and that's increased impermeability. So there are two different time scales in this process, and they do not come out in the old model. So in 2014, some of our collaborators took a phenomenological approach and just resolved these issues by introducing a phenomenological model for the electroporation. Going to the equations. So the electroporation, in the electroporation process, the wavelength of the applied electric field, these are time-varying sinusoidal electric fields, let's say, but the wavelength is bigger than the same size of the cells. So you're at a quasi-electrostatic regime. When you simplify the Maxwell equations, these are the type of equations that you take. You get basically, it's very simple, it's just a Laplace equation, but this is the conductivity rather than permittivity that you would initially expect to get. Then you have the boundary condition, which is at the location of the electrodes at the boundary of the domain, as given by some function. That's where we impose the whatever profile we have for the pulse. And then we have the initial condition, which is uniformly zero in our simulations. Then you have the conservation laws that you have to impose on the boundary of the cells of the membrane here. The first two are universal. I mean, this has nothing to do with the electroporation itself. They are true for when you work in the Fourier domain for Maxwell equations, and then you just write the boundary condition for conservation of current. That's what you get basically. But the electroporation actually comes in when you have this, when you replace this model for conductance of the membrane by this nonlinear equation. Nonlinearity comes because x1 and x2 are two phenomenological fractions for poration and permeabilization that are given by these nonlinear coupled system of ordinary differential equations, and they have to be imposed everywhere on the boundary. So this is the model of Legge et al. That we use, but this is more general. This is actually true for any triphasic heterogeneous system, whether in colloids or whether it is transport of heat, whether it is transport of current or whatever. So from the numerical point of view, there are many different methods to solve this problem numerically. We just go with the Warner interface method. And it has some nice features. For example, it gives you a second order in solution, first order in gradient accuracy. It is positive, symmetric, positive, definite linear system. And most importantly, only the right-hand side is affected by the jump conditions, which is very plausible, and because you don't have to recompute the matrix in the linear system at every iteration. But there is some drawback. The quality kind of depends on the mesh. We'll discuss that later. So this is the Warner interface method, which was proposed by my collaborator, Arthur Guittet, in 2015. This, basically, you start from a Cartesian mesh. You have this interface that crosses the different computational cells. Then you just remove these cells that cross the interface and replace them with a pair of equidistant points. And then you use them as the seeds for a Voronoi tessellation. And then you end up with a Voronoi grid, which is body fitted to the interface. And now you can easily replace for the impose the gradients that you have, the jumps in the solution gradient, and then you combine this with finite volume schema I'm talking. So then you get this discretization. As you see, this discretization is a symmetric positive definite matrix here, and the jump appear on the right-hand side, which were as advertised. So we use Word++ to convert the Cartesian matrix to a volume mesh. Do you have a question? No, okay. So yeah, so now when adapted to the case of electroporation, we impose the boundary conditions that I showed you before, and this is a discretization. We can talk about that later. But as I said, so we don't have any, so basically because of conservation of current, we don't have any jump in the flux. So on the right-hand side, this thing doesn't exist. You see, this thing doesn't exist. And everything about the jump actually appears on the right-hand side, which we have to measure at every time we have a simulation and just replacing the right-hand side here. But everything on the left-hand side is the same through a simulation. Then we are using the linear model for operation. Actually, there are two models that we can discuss if you want. So in one model, it doesn't change, and that's the one I use for modeling. In the second model, it's nonlinear. This one actually changes because this S appears in sigma hat, and sigma hat appears in the left-hand side of the matrix. But for that one, unfortunately, this doesn't help. So let me show you some numerical accuracy tests on a single cell where we can have exact analytical solutions just by solving the equations by pen and paper. And these are previous work by, again, Arthur in 2016, which was a serial environment simulation of this problem. This is my simulation in parallel environment for 3D and high resolutions. And this is a convergence test for the linear model and the nonlinear model. So here we are doing both convergence test in time and in space. In time, we just have every time we divide the time step by 2 in every case. And we just plot them, and we expect that because the method should be consistent, and it means that it should get closer and closer to the exact solution which is shown by this dashed line, black line here. And it does. And also there is the issue with the spatial, for which we just change the level of resolution and level of refinement every time, and we expect again to see convergence to the exact solution, which also happens in both models. So now we know that the method is accurate, is convergent and consistent. So now let's actually do something better with it because we are interested in relevant length scales for cancers, tumors, and things of. We are interested in cell aggregates, 3-dimensional cell aggregates composed of somewhere around tens of thousands or hundreds of thousands of cells, and we are trying to resolve everything on the membrane at very high resolution. And this is some experiments that people do. I'm just showing you some visualization from some actual experiments that people do with electroporation and cell aggregates to show you what the experiment looks like. These are parameters of the model, which are similar to what here people do. And also these are some details about the computational aspects of the model, like the number of cells, nodes, and processors, and things like that, if you're interested. So just to show how, of course, this is parallel code and it scales very well. This is just to show that it scales perfectly. So this is a scaling test up to 4,000 cores. This is on a cell aggregate composed of 300 cells. So you would expect that when you go to 4,000 cores for an aggregate composed of 300 cells, you should get very bad results for communication because the domain is not really that big. But the still is doing a fair job. I think it's quite good. But the actual performance, the actual measure of merit actually is on this case, which is this simulation literally. So you have 30,000 cells at a maximum level of refinement of 10. And this is to show how accurately the cell membranes are resolved. There are more than 3 orders of magnitude in resolution in space. And you still get a perfectly scaling at very high number of processors. And here I'm just showing that I simulated just for the fun of it, is a lattice of 1 million cells. So to make a comparison, this is previously what people could do. That's actually what R2 in our lab. So we are just, the competition is inside the lab. So this was what people had before, and this is this current simulation can do. And this was acknowledged as a state of the art by many actually news agencies. So now let's go back to science. You can, now that you have these simulations, you can go and ask scientific questions, for example, to measure the impedance of the cell aggregate, for which we just compute numerically these integrals. Basically, I'm dividing the difference of the potential in the electrodes divided by the current that is felt at the electrodes, and that's the impedance in the time domain. And now you can make some visualizations of, and here you can see this overshoot, which is actually observed in experiments, is also reproduced in the whole aggregate. Now, people in experiments can make some measurements. For example, they can compute the fraction of cells that are electropermeabilized more than a detectable threshold. So these numbers exist in experiments, and we want to make those such comparisons. So we are basically in our cell aggregate, we do the simulation, and every time step, we compute what surface area of the ellipsoid is electropermeabilized beyond different thresholds, that is depicted here. And then we just divide it by the total surface area of all of the cells. And this is how it evolves over time. This ratio is actually in good comparison with some experiments that we can put in the paper. And these are just some snapshots of conductance values. So these are conductance values. And for example, let's say this white color corresponds to 19,000 siemens per meter. So we integrate this cap of this ellipsoid and divide by the whole area. Another thing which is reproduced in the simulations is the shadowing effect, which is basically you locate the electrodes here and there, and as you go farther and farther from the electrodes, you expect to get less electropermeabilization. That's shown experimentally, and that makes sense also physically, and the simulation results also indicate the same thing. And one numerical aspect of this test here is that, so let me explain the test. So this is a lattice, every cell is identical, and we make the simulation, run the simulation, and we make the measurements on these set of cells here, and then average it for parameter x2, which is the permeabilization levels. And we also do the same thing in the mid plane and in the top plane. We would expect that the top plane and the bottommost plane are in terms of level of permeabilization are identical. So the curves should exactly overlap, which is reproduced here. So it preserves the symmetries that exist in the problem. And you have also lower permeabilization in the midplane, which is also, as I just explained, and observed experimentally. You can ask more questions. For example, you can investigate the effect of the cell shape on the average conductance enhancement of the cell aggregate, in the average transmembrane potential of the cell aggregate, in the average Pouria levels or the permeabilization levels. And just to give you an intuition, you would expect that when the cells have a higher exposure to electric fields, for example, when they're oblate, the surface area perpendicular to the electric field is higher. So you would expect to have higher values of electroporation in all of these different measures. And that's the case. So basically, this was my second project in terms of, that was published in 2019, again in Journal of Computational Physics. So now this is the end of the first part of my presentation in terms of just doing some applications of numerical simulations. Now I want to go into modeling, which is answering more important question of what we do with the simulations. So this is now under review, and this is still available on arXiv. This is the joint work with Samiro and Fredrik. So let me give you a high-level view of the whole story. And that is, every cell in the cell aggregate has a different level of permeabilization, but that corresponds essentially to the transmembrane potential that is induced on that specific cell. So basically, we want to have, if you are able to model the distribution of induced transmembrane potentials on each of the cells in an ensemble of cells composed of, let's say, 30,000 cells, then we have a statistical model for a cell aggregate, right? So the focus of this modeling effort is to be able to recover the statistical moments of the induced transmembrane potentials in the aggregate, and also to be able to look at how they evolve in time. Fortunately, there is something for that. It's called the Kramers-Moyal expansion, which is just the general form of the Fokker-Plan equations, and I'm just showing you here. This W is a probability density function of the observable parameter that you're interested in. The idea is, this procedure is just 3 steps. It's very simple to present. So the first step is just to define some mesoscale quantity. And for us, because we're interested in the transmembrane potential, and the transmembrane potential isn't exactly a uniform number. It has a distribution that can be decomposed into a series expansion, like a multiple expansion. And we show that a dipole expansion is enough. So these cases for us are the induced dipole moments on each surface, on each cell membrane, basically. Then if we are able to somehow come up with a Langevin equation for the evolution of these state variables, and we can make some assumption about the noise term that appears in this equation. We can carry on some averaging procedure and get the Fokker-Kramers model expansion. So that's the general strategy that we want to do. This is quite famous strategy. Actually, a lot of the equations that you already know are derived like this. We can discuss that if you want. So, but to do it in the specific case of cell aggregate electroporation, I want to start from Green's theorem, which is actually the one shown here. This is actually the Green's theorem, a little bit more complicated version of it, where you have some discontinuity in the environment, like the cell membranes that we are talking about. And now the trick is, in this equation, let me just introduce the variables. This sigma is the conductivity at any point. Sigma C is conductivity of the cell cytoplasm. Sigma E is the conductivity of the matrix. Psi and phi are twice differentiable scalar fields in the domain. And everything, and the rest of them is just integrals on the surfaces and the volumes. Now the trick is to replace sigma phi with U being the electric potential of the environment, of the system of equations, and psi by 1 over r being the distance from any point on the cell, on any cell's membrane to any observation point in the domain. When you make that change of variables, all of a sudden this equation simplifies to this one, and on the left-hand side, the solution actually appears. Now, when looking at this, you can identify 3 general sources of electric potential. The first one is integral on the surface, and it at the surface of the membrane, of the surface of the cells, and it actually has this U, the jump in the potential. And the form of it corresponds to the form of the electric potential provided by a dipole moment in a distributed dipole layer, as the people call it in physics. And that corresponds, and the magnitude of the dipole moment actually corresponding to this integral is actually exactly given by this integral. So by looking at the first term, we come up with this definition for the dipole layer of the membrane. By looking at the second integral, I identify this is actually the volumetric the volumetric polarization and the electric field associated to that. And if you have this, then the dipole moment corresponding to this distribution is actually computed by this integral, where tau is the excess electric flux within the cell volumes inside the cytoplasms. So by looking at the second integral, I come up with this equation and this definition for dipole moment. And this is just on the boundaries, and this is just the effect that the electrodes have. So you just keep it as is. Now, because of the way these are defined, there is a mathematical relationship between S and P, and this is shown here, which is they're different by a surface integral of the potential on the exterior side of the cell membranes. Now you can do a lot of averaging and play with equations around and compute the average electric field, average membrane polarization, average cytoplasm polarization, and they give you some generic equations, some generic forms of equations. For example, the average electric field would be given by this. Or, but we keep it like at that point. So let me actually stop here. So what I'm saying here is just some defining some variables. So I'm just defining some polarization variables here and some general relationship between them. Now let's go back and focus on one cell and consider an idealized spherical cell and try to solve the system of equations analytically, just to get a sense of what the equations actually, what the solution actually looks like. So you solve it in the Fourier space, and exactly these are the solutions that you get. This is the jump that comes out of this problem as given by this equation. And as you see, it actually has the form of a dipole moment, some value multiplied by cosine theta, and theta being the polar angle. So this is actually, and this makes sense. So you can also compute the electric potential in the cell cytoplasm and in the exterior, and there are these variables that are everywhere. However, you can also compute you can now go back to these definitions for P and S. That's why I introduced them here. And if we have U, we can compute P, and if we have tau, we can compute S. So we have this U here, and tau is just computed from here. And then you get the P and S, the polarizations in this fashion. And these are actually some linear relationships, and this coefficient is called polarizability. Now you can do some averaging over this ensemble of cells, and the coefficients now become susceptibility coefficients. So this is now the electric field that you will fill in if you're in any point in the matrix, and this is the quantity that we should use in our Fokker-Planck strategy to equilibrate the induced polarizations with this stimulation. So now you can make some diagrams, of course, see how the matrix electric field is affected by, let's say, frequency, increasing the frequency of the stimulation or the volume. volume fraction of the cells in the environment. So I'm going from 10% volume fraction to 65%, and I see that the electric field in the matrix reduces. And yeah, so we can go further and now ask what are the effective conductivity and impedance that come out of this triphasic model. So for that, I would just again compute some volume integrals of the electric flux and define the effective conductivity as the linear relation, as the coefficient of proportionality between the average flux in the whole aggregate and the average electric field in the whole aggregate, the sigma bar. When you do it properly and you average in the cytoplasm, in the membrane, and in the matrix, then you come up with this equation, which is fortunately in the form of this S and P average on all the ensemble, which we already know what they are. We can replace them by the susceptibility we just defined, and we get this general equation for the effective conductivity of this environment. Now, some sanity check. This eta is a measure of conductance. It's the dimensionless number introduced to just talk about the memory conductance. When you take the limit of this to go into infinity, you expect that this has to reduce to Maxwell's relation up to order, because Maxwell's relation is also accurate up to order volume fraction, and this is actually what happens. Then you can compute the impedance by dividing the electric current by the average flux, and that is your expectation for the impedance in the Fourier space. And now you can make some plots and try to play with the value of the membrane conductance at different limits, like 1.9 Siemens per meter squared. You get this with respect to volume fraction, and you get this one with respect to frequency, changing the frequency. But you can also ask what will happen if you increase the membrane conductance because of the electroporation process. And then you will see that basically, as you expected, the magnitude of the effective conductivity enhances in both domains. But that was just characterizing. So far, I've just characterized the stationary solution or the equilibrium solution. I just told you what is the effective conductivity and the impedance of the aggregate. But I'm really interested in to know about the time evolution of it, because we know some experiments are interested in the rate that you get into that equilibrium. So if you look at the boundary condition for the conservation of flux and just integrate over the cell membrane, you can get this equation for the evolution of the membrane dipole moment in time. Now, if you do some normalization by cell volume, which makes them more similar, then you would get this equation for the time evolution of the polarization per volume of the cells. And these are the coefficients that appear. And as I mentioned, this is the electric field in the matrix that we use here. Now, the thing is that different cells have different radii, and they may have different coefficients for let's say, their conductance or their capacitance, and the cell cytoplasm in different cells could be different. So all of these comes into play as a perturbation to this variable gamma and this alpha. So we do a trick basically, and we just consider a distribution for this alpha and gamma, and we define the average values, and we make some assumptions, very crude assumptions that are unrealistic, but that's the first step, about the shape of this distribution. This is basically to say that this comes from the Gaussian ensemble. And then you get this perturbed equation, and now you have this one looks like a Langevin equation with a multiplicative noise term here and an additive noise term here. Taking both into account, you can perform the averaging and you get into this Fokker-Planck equation. So this is supposedly the equation that tells you how the probability density of cell aggregate, of the polarization of the membranes in a cell aggregate evolves over time under any arbitrary electric stimulation as they appear here. And the rest of the parameters are known. Actually, they are physical interpretation. We just derive them from bottom up, right? So then you can exactly solve this equation for the stationary part, and you get this skewed T-student distribution as a general solution of this Fokker-Planck equation. And this will be the parameters that come out of the model. Now, the important thing is that now that you have a distribution function, you can compute different statistical moments like average and variance. And when you do that, you get these results, yeah, right? So these are our predictions. Now let's overplot, and the histogram here is the exact numerical simulation over 30,000 cells. The solid line is the prediction of the model, perfect match. So let's go on and compute do some trick to actually compute the evolution of statistical moments out of the partial differential equation that I just showed you. So we just define averages, different statistical moments as just let's say, so average of x to the power n is just integral of w x to the power n dx, x being polarization, and w the particle density, of course. And then you get this system of ODE that tells you how these statistical moments evolve with time. They have their limit actually, but we can discuss that later if you want. And the rest of the parameters, nu and c, that determine how sharp the TSN distribution are. So nu is here, and c is actually the power of this exponent, actually are related to the rest of the parameters, as you see. But as I mentioned, so the assumptions that I've made about this, about the distribution of the perturbation in the alpha and gamma parameters are very crude. In fact, when you look closer, you'll see that the probability distribution of those variables follows more like an exponential. And for those cases, it is known that the equation has to be modified a little bit by changing the order of the time temporal derivative to some alpha. This alpha could be less than or more than 1. But then there is some arbitrariness here because there are many definitions for the fractional order derivative. We use Caputo fractional derivative because they preserve the number of initial conditions. For example, in a first order, if you are looking at the first order differential equation, you only need one, physically, you only need to have one initial condition, but the other definitions require more than one initial condition. So this is the one that is favored physically, and that's the one we use. Now you can solve the equation exactly as I did here, and then the evolution of the average is given by some equation that the temporal dependence is through some Mittag-Leffler function, which is a generalization of exponential function, which is a little bit skewed of a version of this exponential function. Now let's compare with the direct simulations. So here you're looking at the evolution of the average polarization and the standard deviation of average polarization, of the polarization, right, over time in the simulations. The dotted line, the dots here represent the results out of the numerical simulations. The red line is the exponential model, which you see overestimates the polarization around here. But the other two are numerical and analytic solutions that come out of this model. And you see they perfectly go over all the points. So that's encouraging. However, when we look at the standard the variance, we see that the overshoot that comes out of this model is significantly more than what we get in the numerical simulation. There could be different reasons for it. I'm not still sure what is causing it, but I'm just happy that this signature appears in the evolution of the variance in the model. So qualitatively, I would say that the variance is captured. And of course, the only thing that matters is the stationary value is perfectly reproduced. It's just that this initial overshoot is overestimated here. But another important thing is that the average is perfectly captured. So everything that I'm going to say next depends on this average, and I'm going to claim that is right. Okay, so let's introduce some different electrical simulations. I go with the exponential profile because the Fourier transform on exponential is also exponential, you basically are simulating all the frequencies, and you can make these plots easily with one run. And so you can compute the impedance, the magnitude, and the phase of the impedance given the model that I've showed you before. And this is the Bode diagram, and this is just another representation of the Bode diagram, just a Colcott plot. And you see that as we increase the volume fraction of the cells, this second arc appears to be more pronounced. This is in fact because of the membrane, and this is the first arc is because of the cytoplasm. And as you expect, when you have more cells, this effect should be more pronounced, and it is. But when you increase, now here we're keeping the cytoplasm conductivity fixed at 1 Siemens per meter, but varying the extracellular matrix conductivity from a value of 0.5 to 1.5. Of course, when the matrix is less conductive than the cytoplasm, you expect to get a qualitatively different behavior than when sigma E is bigger than sigma C, right? And that's exactly what happens. We see there's this inversion in the imaginary part of the impedance with respect to the real part when we go from smaller values of conductivity for the matrix to higher values. Now we're changing the conductance of the membrane, and we're going from a low value of 1.9, almost insulating, to a very high value of 10 to the 5 Siemens per meter squared. And as we go to higher values, these are the hotter colors, you see that for higher values, the second arc vanishes. So, which is also expected. because the effect of the membrane will not be the limiting factor against current that passes through the environment. Another issue is when you play with the order of the time and derivative, which actually corresponds, is a measure of how diverse these cells are. We change it from a value of 0.9 to 1.1, 1 being the usual number. And you see that there's a rich set of behaviors, qualitative behaviors that come out. This is actually quite interesting because this is known that in many colloidal systems that are triphasic, this inductive loop, so this loop that appears for subdiffusion, or therefore the less than one, this appears in many fields, and there's still ongoing research on what is the actual cause of it. Also, for example, in the case of some axons in biology, there are some experiments that I cited in the paper that they observed this, but they had no clue what this is, because it basically indicates that there are, for some frequencies, here this side is the low frequency of the Coarse diagram. So at low frequencies, there is some induction that is going on, even though there is no inductive electric element in the environment. And so the question is, how can you play with some capacitors and resistors and come up with some inductive behavior? And here we're showing that a triphasic model that we developed in this part of this research actually has this signature. So maybe that's why. So there are many more results, but I just factored them out in this presentation. And so this is the summary. Very brief summary is that I developed 2 numerical simulations and a mesoscopic model. Questions? Thank you.